Hello everyone. So thanks Dr. Weglein for introduction. And as Dr. Weglein said, my talk is the last talk for today. I just hope this is the last, but not for the least. Okay, so the title of my talk is ISS internal multiple attenuation on Encana Data side. And I just want to show the key points to you at the beginning of my talk rather than at the end of my talk in the conclusion section so that you can know what I'm talking about. We test the ISS internal multiple attenuation algorithm on the Encana Data side. And from that experiment, we learned two important things. First is that from this morning and all previous talk, we discussed the prerequisites of the ISS internal multiple attenuator. But here, I want to point out that besides the prerequisites, we still need the reasonable data collection in terms of sampling and the offset for the data for the ISS internal multiple attenuator to be effective. Second, higher order internal multiple attenuator terms may be required if you have a very strong higher order internal multiple events or energy, like mentioned in Dr. Meihin's talk in this morning. Because we have had the introduction tutorial by Dr. Weglein, and we have a bunch of talks about the ISS internal multiple attenuator. I will not go to detail about to introduce everything again, but we just go through the background very quickly. In M-OSRP, we have a processing chain to process the seismic data from the pre-processing include wavelet removal and reference wave removal, deghost, like talked in Dr. Meihin's talk in this morning. And then we have the demultiple tasks. And then we will have the depth imaging and the inversion after that. For the demultiple tasks, we have surface-related multiple and internal multiple to deal with. In this talk, we focus on the internal multiple. For internal multiple, in M-OSRP, we use the ISS internal multiple attenuation or elimination method to deal with the problem. All talks before me was talking about the ISS internal multiple attenuation, and in tomorrow's presentations, my other colleagues, Yang Zhou and Qiang Ma, will talk something beyond the attenuator, the ISS internal multiple eliminator. From the talks before me, we know the ISS internal multiple attenuation has some advantages. Like we do not know any subsurface information, and we can predict the exact time and approximate amplitude for all first order inverse multiple events, internal multiple events. Sorry, and we can predict all internal multiple events at all depths at once. We do not need to pick the generator or phantom layer or anything like that. We also know that we have prerequisites. We need to remove reference wave. We need to remove the source wavelet. We need to deghost, and we need to remove first related multiple before we go to internal multiple. Here is just a cartoon to remember the idea of ISS internal multiple attenuation. Here we have a W-shaped internal multiple event, and it can be decomposed by three reflections, satisfy the higher, lower relation. And we just combine the three sub-events or three reflections to get the prediction of this W-shaped internal multiple events. So you have seen this formula several times today. I will not go into detail. This formula just tells you how to combine this three B1 term to get B3 term. It's internal multiple. And this formula is for 2D case. We have also 3D case, a 3D version of this internal multiple attenuator. Here are some previous efforts to apply ISS internal multiple attenuation on field data. We have no intention to make a comprehensive full list of all efforts on this topic. Here are just some major ones. First, Mason 1999 applied the ISS internal multiple attenuation on the streamer and the streamer marine data. And then Mason 1997 and Weglein 1997 extended the ISS method to free surface and to free surface and internal multiple on the ocean bottom and the land data. And 2010, my colleagues in Saudi Aramco and I tested the ISS internal multiple attenuation on Arabian Peninsula data field, land field data when I worked in Saudi Aramco at that time. Recently, Dr. Tarinki showed an example of ISS internal multiple attenuation on land data also. Now let's look at the Encana data set. Why this data set is interesting, and why we want to test our algorithm on that data set. First, this is the Encana data set. This is stack section. We can see that all events are very flat or fairly flat. And I'm sorry, I'm not a geologist, so I cannot tell you the whole story about geological background about this data set. But I can tell you what I know about that and why this is interesting for us. There is a co-layer in vicinity of 1 second in this data set. It's a major generator of the internal multiple, or it's a strong reflector. And we should have some rift in this area just below the core layer. We learned that from the web log in this area. However, the rift is invisible in this data. And the reason must be some strong internal multiple interference that makes the rift invisible. So our goal is very clear. We have just one goal, to make the rift visible again, clearly, by just remove the internal multiple internal multiple energy. So as I mentioned, in 2010, I tested the same algorithm on Arabic Peninsula dataset. That dataset has better data quality. Just because this dataset, I forgot to mention, is this dataset is collected in middle of 1990s. It's kind of early vintage. So this dataset does not have some advanced modern acquisition technology. So the quality of this dataset is not as good as the Arabian Peninsula dataset I used in 2010. However, we have a very clear goal in this dataset. For the field test in 2010 about the Arabian Peninsula dataset, we do not have one clear goal. We did remove a lot of internal multiple energy, but we cannot find one goal, just one target to justify we have anything done. We just finished the job. Here we have that goal, a single goal, very clear. Now I just show you the acquisition parameters. As I have mentioned, this is a kind of early data. It's collected in middle of 1990s. It's a 2D CMP survey line, which consists of 146 CMP stations. The data includes the traces from 4 different azimuths. I will show you the map later, so you can know that. And the offset interval in each CDP gather is 62.5, and we have only 32 traces per gather. This is a very low fault compared with any modern dataset, land dataset. The time sample interval is 2 milliseconds, and we have 1001 time samples in each trace. So here is the acquisition geometry. It's the map view. It's just a view from top of the map. The pattern, the red dots, we should have dots here, but for the resolution issue, resolution reason, we cannot see the dots clearly. But the red dots just represent the source location. The blue dots just represent for receiver location. this pattern is kind of complicated to understand, so I will just decompose that so that you can easy to understand. We just look at the first CMP gather. This is one CMP gather for one azimuth. This is the first gather. And as I said, the blue dots just represent for 32, the blue dots represent for 32 receivers here. And the red dots represent 32 sources location here. And in the middle is a CMP point. I just made this cartoon so that you can further clearly understand. We have the receiver on one side and the source on the other side, and the CMP middle point, CMP point in the middle of that. So this is the geometry for the first gather. Then for each CMP gather, for each CMP location in the middle of this, we have 4 different azimuths. So for this CMP gather, so this CMP location, we have 4 gathers. And then along this axis, we have 146 different CMP stations. So we have 146 this pattern repeated along this direction. So finally we get this. After we have seen the data set, we need to make the decision what algorithm we should choose or we should use. Here is the decision. 2D versus 1.5D. So the data set is a 2D survey line. Also, they have 4 different azimuths, but the middle point, semi-point, is just along one line, so this is a 2D line. And if we want to use the 2D ISS internal multiple attenuation, we need a full coverage geometry. Means that from each source station to each receiver station, we should have a trace. But we have very limited fold for one each CMP gather. We have only 32 traces for each gather. That means if we want to obtain the full coverage geometry, we need to do a lot of extrapolations. That is not only we need to make a lot of effort, but also we need to make up a lot of data. That is not reliable, or we do not feel comfortable about that. We just make too much data. In addition, we have seen that the subsurface geology structure in this area is pretty flat. So we just choose 1.5D ISS internal multiple attenuation logarithm rather than the 2D, the full 2D. What does the 1.5D algorithm mean? We just comes from 2D. This is the formula we have seen a lot of times. And 1.5D means that a 2D source, but with a 1D Earth. Like we assume the Earth only have variation with depth. We do not have any lateral velocity, lateral changing. Or we just assume the medium consists of only horizontal flat reflectors. Under this assumption, the B1 term from the symmetry has a delta function here. And when we do the integral over K1 and K2, we can get the 1.5D ISS internal multiple attenuation just because we have the delta function here. My colleague Xin-Lu Lin will explain about this topic more in her tomorrow presentation. So like I said, because we have 3 B1 terms, so we have 3 delta functions, the Dirac function. After the integral, we will have the Kg equals K1 equals K2 equals Kf. So we use one letter to represent that. We just use the Kf because they are all equal. Here is the 1.5D first order ISS internal multiple attenuator. And we just use that formula to do the prediction. The code I used is a revised version of 1.5D code of Tyler Perinki's work when Tyler works with us in 2012, I think. Tyler's code can be found in M-OSRP website, which Dr. Minhan has shown you the the link of the address and how to log in on that. So after you log into our website, you can go to research and projects and coding projects. The code is the second item on under the coding project, just this one. After we introduce the algorithm, now let's look at the result and let's do some discussion. Here we just come back to the stack section of the input data. We have seen that at the data section. And here is the output after the prediction and after adaptive subtraction. We can go back and forth, and we will find that we did remove some internal multiple energy in this area just below the 1.1 second, the major reflector. So that is not a bad result. If we look at the difference, we will find that we did not do any peak or any phantom layer. The result automatically comes like before the major generator. We have almost zero. We do not have any. We do not hurt any primary or any event before the major generator, and we remove the lot of internal multiple energy below the generator. This is good. However, the result is not fully successful because even after the attenuation, internal multiple attenuation, we still cannot see the reef clearly. So that is not fully successful. Now I just want to show three gathers. Just want to show some pre-stack result. This is the three gather of input data. This is three best gather I choose. And here is the prediction internal multiple in pre-stack domain. So you can see the prediction result is not perfect. And we have known that the result is not entirely effective. What's the reason? Here is some reason we think. First of all, the data has very limited fault per gather. It's only 32 traces per gather. And nowadays, I think it's easily you can find the data gather 10 times about this fault for each CDMP gather, or even more. And the amplitude in the in the offset part for trace for each gather is kind of low. What does that mean? I will show you. This is a Wiggle plot of one CMP gather pre-stack. We see that this is the major reflector. We have the low amplitude zone in the near offset here. And if we have a flat reflector, the near offset is critical to predict near offset multiple. Near offset input is critical to predict near offset input multiple. So we think that is part of the reason we did not get a perfect result. And we have, of course, the environmental noise and the bad trace. We cannot complain too much about that because this is land data. This is Europe, right? For land data, we just have the noise, we had a bad trace. But keep in mind, if you have only 32 traces per gather, this one will just cause some bad thing to you. You do not have the redundancy to overcome that. And another thing is that because we, any question? Okay. Another thing is that we have a very strong reflector at the 1 second. It's kind of similar to the resurface situation. Because we have one strong reflector, we will have higher order internal multiple, not only first order. And in Thomas' talk tomorrow, we will see that if we have the multiple in the input data, because the data contains multiple, of course, or we will not do the job. We have multiple for the input. Even we use the first order internal multiple attenuator, the output will have the higher order internal multiple. However, the amplitude will not be correct. Furthermore, the priority may be flipped for some order. Someone may argue that since we have the output for the higher order multiple prediction, we can use the adaptive subtraction to subtract not only the first order internal multiple, but also higher order internal multiple events. But keep in mind that we do the adaptive subtraction window by window. If within one window, we have both correct priority and flipped priority, the adaptive subtraction or the adaptive filter cannot fix that. So this is why we think if you have just the normal case, you have higher order intermultiple energy, but it's not severe, you can use the first order intermultiple attenuator to deal all of them. But if you have severe for higher order intermultiple energy, maybe you want to use the more than first order intermultiple attenuator. Maybe you want to use a higher order intermultiple attenuator to deal with. So you can better remove the higher order intermultiple energy from your data. Oh, yes. Now let's draw the conclusions. Early, a radical onshore SS intermultiple test has reasonable multiple offset aperture and produced a successful result. This Encana Data test in here, I showed here, was a kind of an early vintage. So it has a much smaller maximum offset, and that produced a less successful result. However, the current typical acquisition for marine and both marine and land exploration, I think will be adequate for ISS intermultiple attenuation to be effective. So we do not need to worry about that if you have a current data or modern data, not the data in 1990s. And as I mentioned that we learned two important things from that. First, besides the prerequisites, you still need a reasonable collection or reasonable acquisition to get a good result. And second, if you have severe higher order intermultiple energy in your data, maybe you want to use a higher order intermultiple attenuator to get a better result. And we would like to thank David McKee, David Bonner, and Encana for providing the data Encana set and to allow us to present the results. We thank Paul Tarinki for lots of very helpful discussion. And we will thank Bill Goodway for long-term support for us. And of course, we thank all M-OSRP sponsors for your support and encouragement. Thank you very much for your attention. Please.
Well, first of all, a comment. I'm very pleased to hear a presentation where you emphasize the importance of the data acquisition, because that is certainly a key prerequisite for all these data-driven methods, and it's not something that should ever be overlooked. And then I have a question. You mentioned at the beginning of the talk that there was a well log available.
Yes.
Did you make any attempt to compare your before and after results to the well log?
Oh, I think probably because maybe David McKee do not want to show us the answer, so you can do a fair comparison. We do not have the well log. We know that the target should be the reef, but we do not really have the well log for that.
All right, well, maybe you should ask them now that you've done the prediction.
Yes.
And, that might give you some better ideas of,
yes.
of how it could be improved.
That, yeah, probably this, they maybe think that it's kind of cheat if you know the answer and you can match the answer, right? So it's just a blind test. You do not know the answer and see what you can do. And after that, we have the result. Result is to see the answer, and then you can tune in your parameter, like you do the adaptive subtraction, and you do lot of things you can play with to match the result. Please.
I guess you, under your policy, did you use the adaptive subtraction or not?
Yes,
you did.
Okay. I did. Oh, I
single trace by trace or multiple trace?
It's a window.
It's a
window, both in the trace direction and in the time direction.
Yeah. And so you said, you talk about the degradation. That's really good. And you said your CPP spacing is 62.5 meter or 6.25?
6.5.
6.25.
Sorry.
Okay.
I'm sorry.
Excellent.
So the adaptive subtraction was done in which domain?
Is
Common chart, common offset?
That is in the same domain, CMP domain. They keep in the CMP domain. They do not do the result.
So you said, like, I would have liked to see a common offset, like
Yes.
you showed the common stack picture,
Yes.
like before and after. And you said you were having struggle with the near offsets.
Yes.
So I would have liked to see what were you doing in the middle offsets, where you still have it's a flat reflectors, so you still have the far offset for you is 2 kilometers here, probably roughly.
Yes.
But somewhere in 1 kilometer offset, what kind of predictions were you getting? Because there the amplitude,
You mean the near offset?
middle offset, kind of
Middle offset.
yeah.
Middle offset, I think is okay.
Oh, but it goes again, I mean, to predict the legal offsets, you need the offsets to do so.
No,
So
yeah.
you will be corrupted, by all means.
Yeah, so how far I could go, I would want to see,
That's a good
because the
question.
stack kind of can kill you a little bit, because the stack is a near offset dominated in this layer.
Yeah,
So-
but when you go to the offset, I mean, it's an offset to try to look for differentiation between the modules and their parameters. In this case, we don't have any, so the common offset is really challenging the way to do subtraction.
That's right.
Because then your subtraction is going to try to kill everything no matter what. It's an initialization problem. So you try to go for places that you have a better separation between modules and their primaries. Small question, quick question. For the near offset, have you done any kind of extrapolation? Because I saw this image with 32 traces per CMP, but when you show you a near offset thing, it's
Yes,
way more traces.
The truth is that we get the data from Encana. They did the pre-processing. And I think they did some interpolation or extrapolation and also some other processing. Because this data is very old, so no one can figure out what exactly done before this data set. But I think so.
Yeah, I also noticed that your CMP is quite ageist.
Yeah.
So I guess if you have ageist data, then it's going to be a major problem for your prediction. And I also saw a lot of strong linear noise.
Yes.
Low velocity noise. Did you do anything to remove those before when you do the prediction?
No. You see that because for my test and that one will not cause the most severe problem for that one. Or it's not the major reason to read a bad result.
Well, one of the reasons.
Okay. And I also I agree with your comment that if we do the subtraction in common offset domain, because that is flat, it may have the better result because we have the window. The whole event in one window is flat. But here, because some offset is fine, so we do not want to just get nothing in that offset, so we just do that in CMP.
So I have a follow-up question. It could be the impact of the batch processing on the removing the ground roll because ground was slow.
Yes.
So you try to reduce the ground roll energies and then it can harm the primaries.
Yes.
It can cause a problem with the near offset.
Yes.
So do you have some sensitivity analysis about the noise and separation?
No, because that data is compared after the whole
How
process.
about the synthetic data?
Exact data,
Yeah,
I didn't do that in this case.
How did this data meet your prerequisites? All the prerequisites that we require. Did you check that?
Not at all.
The data was given to us, and so it's here. But I would, following that, these comments, within the sponsor group, you have a data which is more current in terms of acquisition. You have a challenging generator and a clear target that you know that we won't. We would be very interested to test more adequate acquisition type. We would more than appreciate that opportunity. I think this was a good, for the reasons that Charlie mentioned, because of its relative simplicity of the generator. But the generator is so strong, you have a high order ringing a lot. It's not one first order multiple. So we're looking at two things. We'd like to work with Total and with Chico on the central North Sea. The whole ringing going on. Bertrand are looking at that for some of the things you'll see tomorrow, which give us a small degree of confidence that we might be able to help. But we'd also like where it's there's a very strong generator and a clear target that we won't know, but you'll know from a well. And we'd like to test, but with, to Bill's point, processing can make the data that you don't have. These extrapolation, interpolation is dangerous, complicated.
Art, do you have any intentions to work with the seam data set, the land seam data set? Because that would be a nice example.
It would be. I
Uh,
think Tim is involved, and Mike Aristoglio, is that right?
Well, I am as too.
Okay.
I'm as well.
We would welcome that.
I mean, this is a, it's nice to see a real data example, but this is a kind of a non-standard land acquisition
Yes.
and would be a very, in my opinion, a very challenging data set to work with. It might be easier to start with one that's a more traditional acquisition geometry.
Now, the seam data, please remind me, I think it was aimed for imaging
Yeah.
issues. Where that earlier, much earlier, Smart JV, they were aimed for multiple issues, so they made sharp boundaries, where it seemed to make things work better, made things smooth, whether the earth's smooth or not. Well, we would like to look, but it might not be realistic to the issue of rapid change that generate multiples. But Ted would like to look and appreciate the comment. So, Joan, excellent.
Thank you very much.